Thank you very much for being here. Thank you very much for organizers inviting me here. So I will talk about the machine learning, Cayley graphs, random walks on them. So that quite corresponds to what Anatoly Moiseyevich was doing. And so this is a kind of joint work, even crowdsourcing project. Many people, many of them quite young, participated. And first, let me mention a little bit my personal remembrance with Anatoly Moiseyevich. So my first meeting with him was related to this paper, which is with Andrei Kunkov. Oops, I'm sorry. It's, I think, very famous paper, a new approach in the representation theory of the symmetric group. So if I would need to say one word about this paper, I would say unbelievable, if two words, unbelievable miracle, because representation theory of symmetric group, it's something like studied maybe from 19th century. Lots of famous mathematicians were working, and what Vershik and Kunkov proposed, like they write in the first sentence, new, simple, and direct approach to the representation theory of symmetric group. So for me, it was something like unbelievable, at least when I was quite young, but even now I don't fully understand how they come up with these ideas. And so for the long time, I wanted to establish connection with Anatoly Moiseyevich, but since he was in Leningrad, I was in Moscow, and I was quite young, and he was already kind of a leading mathematician, so I was a little bit scared. And at some point, our joint work with Vladimir Rubtsov, who is here, with Dmitry Talalayev, Leonid Rybnikov, Grigory Ufalkoy, we found something like related to this work of the Anatoly Moiseyevich. We found some deformations of the Hamiltonians, which they propose in their work. So I thought at this moment, okay, this is my chance. I want to write an email to Anatoly Moiseyevich, and I was visiting St. Petersburg for one-day seminar and tried to meet with him, discuss some questions. And it's like writing an email to the God, you do not really expect the answer. But it was my great surprise that he answered me quite soon and says, yes, okay, I can meet with you. We can meet at the university, or you can come into my house and we can discuss at my apartment. And so we discussed maybe several hours about this and related topics. I remember that he says that very interesting work he is doing with Natalia Tselevich, who is here. And so for me, it was kind of, my remembrance, it was very inspiring. It's not only he was a great mathematician, but he was able to hear you, to hear something like new things, which maybe not so to his immediate interest, but still he was able to kind of give some advices, was open to new topics, and was very inspiring after, I remember, after he exited his apartment, I feel like, you know, you feel kind of a wings, just that, okay, Vershik is interested in this work, okay, that maybe we are doing something good. So we have met with him several times at the different conferences later, and it was always very inspiring discussions with him. So actually, when I started to do this work about the Cayley graphs and machine learning, I thought he would be the first person with whom I wanted to discuss this. Unfortunately, he passed. And so it's my great honor to be here to present this work, which was partly motivated by his works and his ideas. Now, let me start. So let me first explain the task which we want to solve. I want to explain it in the three equivalent ways. The first slide is the most simple and fun way. We need to solve the puzzles. We want to create a neural network which will solve puzzles, cubics or some other puzzles. So you give us the puzzle, but not mechanically, but in the group theory terms. We should train our neural network, and then it will be able to solve the puzzle. Some point is, for the moment, for each puzzle, we need to train a new neural network, which will be, so we should be reasonably fast. But we are reasonably fast. Now, so just to advertise a little bit results, so for the moment, we can solve cubes up to 5 by 5. And so one of the measures how good we are, it's how many moves we need for the solution. And so now we are beating everything in the world for the cases of the 4 by 4 cube and almost for 5 by 5. So it's not difficult to solve the cube, but what is the problem is to have a universal method which works for any permutation group, and in particular for the group we are beating the methods which are specific only for Rubik's cube. So now let me rephrase the same task in more mathematical language. So this is, we have a permutation group, we have some generators and given element. So the task is the standard mathematical, decompose this given element into the product of the generators. At the moment, we do not require the decomposition to be the shortest one, not necessarily optimal, just some. So for our system, you can input any permutations and any as a generators and any element.
Excuse me, what then it means that you are given an element? How is it given if it's not given as a product generators?
Yeah, it's a very good question. So we are now working with very explicit form of given, not the abstract group with generators and relations, but just you give the permutations in the form of the number. So it's
yeah, it's a permutation. Yeah.
Okay. Yes. So everything is given with the permutations. Or another case, it can be matrix group, and you given explicitly given matrices. Yes. It doesn't matter, but we need some explicit input. It should not be generators and relations, at least for the moment. Oops, I'm sorry. So how it's related with the cubes, just maybe everybody knows this, but just to mention, okay. So this is a Rubik cube 2 by 2. You can put it on the place, just numerate all the tiles here, and so each rotation is just gives you a permutation. Yes. So any puzzle defines a permutation. Yes, and so the problem to solve the puzzle is exactly to decompose given element into the product of the generators. Another reformulation which we'll use in this talk, it's with a Cayley graph. So the reformulation is the following. So we want to find a path on the Cayley graph. It's exactly the same problem. Why? Not just standard definition. So the nodes of the Cayley graph are elements of the group. Two elements are connected if there is a generator such that you apply to one element and get another. Yes? And so the most important fact is that any path on this graph corresponds to the products of the generators. And so if you have path from V to A, it is the same that you can multiply these elements and get another. So finding path on the Cayley graph, it's exactly the same as decomposition problem. Just here is some example. If this is for the Cayley graph for the group, and what we should mention, each color represents each generator. So in this example, we have 3 generators, and green generator, green edge, it's one generator, red edge, another generator, blue edge is another generator. Okay, so now a little bit for the context and for the complexity of these tasks. So it was proved in 80s that finding the optimal shortest solution is NP-hard problem for generic permutation group. Moreover, it was proved more recently that even for one group like Rubik's group, for example, it will be NP-hard problem if you consider all the cubes of all dimensions. And these theorems proved for many groups, not only for Rubik's cube. Moreover, what is maybe interesting, even for the standard 3 by 3 Rubik cube, if you want to solve it optimally, that's a really hard problem. The first algorithm appeared at 97, and now it's time to work something like 1 cubic per half of the day. More advanced algorithm was in 2013 by Rakitsky, where in the work was computed the diameter of the Rubik cube with lots of computations. 26 CPU years donated by the Google. Now about what is not optimal. So not optimal, there is a Schreier-Simms algorithm and its gap implementation. But it provides quite long representations. We want to give shorter ones. And for specific choices of generators, like the Rubik's Cube, for example, you have some algorithms which are particular for this group. And this is for not only Rubik's Cube, but it's important in biology, for example, and for many biological tasks, there are known algorithms. And there are machine learning works devoted to this problem. Actually, there are only two main works. This is DeepCube and AlphaGo. They were devoted specifically to 3x3 cube.
For arbitrary groups, is this algorithmically decidable?
I'm talking about permutation groups. For permutation group, finite permutation groups, it's yes.
Oh, then yeah, just by exhaustive search, right?
But for example, yes.
Right.
Yes. But Schreier-Simms is a more clever way, but still it's not very effective. Okay, so now this is the key slide. So now I'll try to explain the approach. So the idea is quite simple. So basically we have three steps. First step is related to the random walks on the Cayley graph. So first we fix the length of the random walk. For example, all the random walks will take, I don't know, 20 steps, for example. And then I'll generate millions of these random walks. Each of them is 20 steps. But there will be millions or billions, actually. Yes? All of them starting from the identity. So I'll create the pairs, the element, which is in my case permutation, and integer number k, which is number of steps random walk achieved this element. So this is pairs element and integer number, how many steps I need to achieve it by random walk.
But if you achieve it by two different ways, you keep the minimal one, or?
That's a very good question. So I actually cannot do anything because well, I can do minimal. Yes, it's better to take minimal. But in practice, if the group is very big, it happens very rarely. But on the other hand, it's a great problem for us because theoretically it can come into 20 steps, 21 steps, and this creates a problem for training the machine learning model. Because once you said this blackboard is green, another you say it's white. And machine learning go a little bit crazy. So that's one of the problems which we need to discuss.
You say you have random walk, so it means that on the next step you can go directly back.
Exactly. For example, yes. So this is one of the main questions, and I hope maybe to get advice in this audience. For example, we can consider non-backtracking random walks, so they will not go one step further. We can a little bit increase this. For example, I can remember several steps and forbid to go into any step position where I was 10 steps above. But then computational cost increases for that. I need to store all these elements, and so this is a trade-off. Yeah, so, and it's not clear. So this is one of the problems for which I need advice, how to generate in the better way. I will discuss it later. But for the moment, it's working with just simple random walks. You can just, yes, non-backtracking sometimes is go back. There is some problem, but it's typically a rare case. Okay, so the next step, the training the machine learning model, so the neural network. The input is these permutations which we generated. And we want to predict this k, number of steps. So first we generated lots of examples, billions of the examples, and now we put them into the machine learning model. And we ask machine learning model, can you predict me from this, can you train and predict from the given permutation this number k? This is typical, yes?
I'm sorry, but this doesn't answer exactly the question that you posed before, right? It doesn't give you the competition, it just says you what's the length.
Yes, because we need the other step. It's not the end.
Okay. Mm-hmm.
Yes. So we are giving. So we are training the neural network such that it will approximately predict the number of steps random walk will achieve this state. Yes. But actually, random neural network will create. It cannot predict precisely. What I'll get is a very huge mistakes in this prediction. So I cannot use this to decompose the elements. So the output of the neural network is some estimation of the length, but this estimation is not very precise. That's why we need another step, graph search algorithm. That is very simple. So we have a graph, and for each node, we have the prediction of the neural net, which says what is approximately the distance to the destination. So if I am standing, for example, in one node, I can look all the neighbor nodes and look for the prediction of the neural net for each neighboring node. And I will choose this neighbor node where the prediction says neural net says me most close to the destination. I will go there. Again, I am looking all the neighbors, and I am choosing the one which is neural net says me prediction is closer to destination.
And how does the neural network extrapolate from the original data to distant?
Yeah, but for permutation you have just the number. You compute the number of inversion, then it's real length.
It is for the standard generators of the where the generators are the transpositions neighboring. I am working with absolutely arbitrary generators which you give me as an input. You can choose any generators. It's input. Okay?
Right. So if I understand how machine learning works, basically your neural network creates some kind of function from some family that approximates the given data set and then tries to extrapolate it into other new inputs, right?
Yes. But extrapolation, in some sense, is automatic. So, because my neural network is a function where you can input any permutation by definition. Actually, even not permutation. You can input any n numbers of even complex numbers or real numbers. It was trained on the permutations, but the input can be absolutely arbitrary.
Right. But
all the zeros.
Correct me if I'm wrong, but my understanding is that there are many different ways in which you can organize this training process. There are some moving parts.
Exactly. That's a kind of our skills of the machine learning, how to achieve it better. It's a lot of.
You're a machine teacher, not machine. Yeah.
Yes.
But you are not revealing how that kind of sausage is made, correct?
I can tell you all the details, but it's. I mean, yes, but there are. I mean, that's a kind of kitchen of the machine learning, how to create this. So it's, yeah. I don't say that we have done this perfectly. I think that kind of next we will improve it. So there are lots of questions to be improved. Just let me stress one thing on the generality of this approach. So it's not related to the Cayley graph. It can be for any graph such that on the node of the graph you have, for example, vector or matrix. We need only the input for the neural network. And input can be actually arbitrary. Then all the steps you can apply. Yes?
Wouldn't it make more sense to look at the small ball around your point and look at the minimum among the nodes within that small ball, not just ball of radius 1, but a little bit bigger? Not the immediate neighbors, but neighbors of neighbors and neighbors of neighbors of neighbors?
Just a moment. At what step? So typically, at the first step, I'm running for the random walks. We should.
Step three. Step 3.
Step 3. Exactly. But I wanted to discuss it later. It's a kind of course. So what is described here is just a simple idea but it's not what we really do. I will explain it. Yes, and
this is just steepest descent.
It's called greedy search.
Probably in step 3 you should use the simulated annealing, otherwise you get stuck.
I will explain this if I have time quite a bit. Yes, so, but that's just the idea. It's not what we really do. Okay, so now just a little bit advertisement of the achieved result. So for example, for cubic 3x3 standard, 98% we can solve optimally. So it's like almost achieving the optimal. So previous was 60, something like 4x4 and 5x5. Machine learning before us was not able to solve. We are solving them, and these are groups of the very huge size. And we are beating, for example, gap in the length of the solutions. Just a remark about the example. So if the group's size is something like less than billion or billion squares, it's not interesting because we can do brute force. So we are interested in something like 10 power 50 or something like that. Otherwise, you can do something like a brute force. Just maybe to add this for the explanation, so source of inspiration is this AlphaGo AlphaZero system, and so let me stress that the task playing the Go game or chess game is almost the same, So what you have? You also have a graph. It's not a Cayley graph, but it's a graph of all the positions, which are nodes here, and edges are moves. Just moves between one or two positions. So you have a very huge graph of the game. What is the goal of the game? It's just to find a path from initial position to the positions which are marked your victory, you win. So it's exactly the same task, to find the path. The only difference is that these tasks are more complicated because we have a second player. So it's a kind of, you make a step, but then positions change independently of you because second player made some move. So this task is more complicated where you have game. But essentially all the other things are quite similar. So all the ideas quite related, and we are motivated by their work. So how they train their neural networks to play the Go game? They play with itself. And this is analogy with the random walks on the group. Yes, it's more or less making the random moves, yes, at first. But then you make moves guided by your neural network. But the same we can do here. Again, one of the key adventures or discoveries of this AlphaGo team from DeepMind was that they combined two things, neural network and graph algorithm search. In their case was Monte Carlo tree search. So the combinations of the two things, neural network and Monte Carlo tree search, allowed them to win the Go game, which was sort of unbelievable before. So now let me stress one of the points. So what is important in this thing, that why do we need the neural network? We need the neural network because it can able to generalize. So in the training set, you show it by the random walks only small number of the positions. So you cannot show 10 power 75 positions. That's almost the same as atoms in the universe. So what you do, you show to the neural network only small fraction of the positions. And then you hope that it will generalize somehow, that this extrapolation to the other positions will work. That is hope. There is no theorem that will work. You just need to check it case by case. Now let me give you examples and explain the difficulties which we have. So the difficulty is that predictions of the neural network, they're not quite good. They're quite really bad. So for example, here, this is number of the steps which I'm doing for the random walk. For example, I am making 30 steps. And this is this pink color. It's the predictions for the neural network, which should be ideally 30. All this pink color should be 30 ideally. But you see the predictions, they go from 20 to even I don't know where. So there is huge variation between the predictions. They are not quite exact.
But the maximum is nearly close to 30.
At this point, this is actually quite bad thing because all they concentrate here. That means it is the states which are quite far by the distance, they are predicted very poorly. Machine learning model cannot predict them, and something it says that I cannot predict, I will give you average distance. So roughly speaking, all this, that many these bell shapes are concentrated here, it's something bad. It shows that machine learning actually cannot predict and say, I'll give you the average prediction overall. The good predictions are here. For example, it's not clearly seen, but the first orange, you see, it's the peak here. Oops. Okay. But things are not that bad. If we look on the average picture would be quite good. So that means that if we take, for example, 20 steps of the random walk, but we run here something like 10,000, and average the predictions of the neural network, average will be approximately 20. And but here you see the variance. So it's a kind of average is 20, but there is huge distribution. Okay? And this is, for example, another example that we are just running for the one and another random walks for 40 steps, and we compute the prediction. So you see it's more or less not so bad here, some kind of mistakes, but here it becomes more complicated. Yes, so neural networks gives in average not so bad predictions, but they are not precise enough.
But do you understand if you have huge group, then the typical element will have length equal to the diameter of the group?
Yes, 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 exactly, yes, exactly. Yes, 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 yes. So that's why we, for the moment, we cannot solve, for example, 6 by 6 cube. If it's going bigger and bigger, we need more training, more GPU. I don't know, but no, it's a difficult problem. Yes.
This is a little bit like predicting the weather. You can predict it for 2 or 3 days, but then.
Yeah, well, but
yeah. So it's the things should not scale not on typical element, but element of sufficient small length. Yeah,
that's right.
Yeah, because typical element will be all of this big length. Yeah.
Yes. So, but it's better to discuss it. So, yes. Now I want to a little bit discuss the growth of the groups, and in the case of the finite groups, because for infinite groups it's very well studied, but it seems for finite groups it's not so well studied. And I want to give some intuitive picture why all these problems is quite difficult. And this is exactly, Maxim, the question you have asked. Yes, so this is people calculated with the help of the Google for Rubik's Cube 3 by 3. This is exact number of the positions in the logarithmic scale. So this is logarithmic scale, but actually almost all is nearby the diameter. So for Rubik's Cube 3 by 3, it's 2 steps before the final diameter. And here we have almost all the states. Yes. So actually, if we look on the similar picture for the other groups, it will be quite similar. So first you have something like growth, which is almost exponential, and then you have a sharp, abrupt of this growth. So as far as so it's easy to understand why we have the growth almost the exponential, because if you choose the random elements, there will be no relations, at least you do not expect. And so it works like a free group for which the growth is obviously exponential. Yes? But why this so abrupt this happens? As far as I understand, there are some works have been done on this, but as far as I understand, it's not clearly understood. this picture is typical when you choose random generators. If you will consider the abelian group, for example, the picture will be different, as we'll discuss a little bit later. So now some nice analogy. So let us flip the picture which I have shown you at the previous slide, and think that, so now we are here at the kind of typical element is somewhere here. So you can imagine it's like a ball. And so analogy that you should move this ball from here to the most topmost point. But that is quite difficult because the number of the positions, it's growing exponentially. Roughly speaking, the number of positions at this point is 10 times or 13 times more than at the previous point. So
maybe this happens just like a phase transition in sense of Gromov. So when the length of commutation relations is comparable to the length of the word.
But that's a good idea. I haven't thought about this, but maybe yes. But just let me explain why it's difficult to solve the Rubik's cube in this picture. So number of states, which is on the position, on the distance, for example, d+1, is 10 times bigger. So you need to make a step in this direction, near to 0. But it's 1 out of 10 steps. So you should make a choice, 1 correct choice out of 9 incorrect, something like that, yes? And that's why you can think of this picture as like a ball, which you need to move here. Actually, our neural network should move it here. It's a kind of like electric field or electromagnetic field, which fights with this potential wall decline. I think that's an analogy, but I think it's quite not good, quite good. Now, let me, about the growth in the finite group. So when I search for the papers, actually not so many papers are devoted to the growth in the finite groups. One of the papers which I found is Anatoly Moiseyevich and Andrei Milutin, who is here. So this is related to the growth in the Heisenberg group. What they found that if you choose the generators which are not symmetric set of generators, but that means without inverses. So 2 generators of the Heisenberg group without inverses. They found the very nice combinatorics, as far as I understand. Andrei can correct me, but this is not what, for example, we are typically considering. This is the, for example, we wanted to look at the Heisenberg group with a standard generated set which includes the inverses. So we computed it by the computer, and we have seen such a picture. It really should mean something, but when we searched for the literature, it was strange that we asked questions, massive flow, so on. It seems no one was able to give the explanation why the growth of the Heisenberg group, finite Heisenberg group, is like this, what we see here. So the explanation found by Misha Yevseyev, who is now student of the Grigory Alshansky in Moscow. So the explanation is the following. So here you see the first period, which is exactly like for the infinite Heisenberg group, which is quite well known. But then you see this is almost straight lines. So how to explain the straight lines? Actually, this is straight lines come from the abelian group. You can consider the projection of the Heisenberg group to the abelian group Zn power 2, just factorization over the center. And the point which Misha discovered that this projection have very good metric properties. That means all the fibers are on the same length. And so essentially, the growth of the finite Heisenberg group from some point, it's almost the same as the abelian group.
Oh, so vertical direction is logarithm?
No, here it is exactly the number.
Not logarithm.
Yes, it's actual number. It's for example, if you look on the plane, so the ball is like this, and so number of points here is exactly proportional to n. Yes, and so that is we exactly see the linear growth. So this is just the effect coming from the abelian group. So we were interested to look in the cases with the growth more precisely for some other groups. And so the natural thing to expect, as far as I understand, for me at least, that if the group is close to abelian, for example, like a nilpotent group, we should expect something like a Gaussian approximation of the growth. Why? Because for the abelian group, at least for the standard generators, it will be like that, because it's kind of the product, the growth will be the product of each component. So the product of the polynomials. Polynomials are essentially, product of polynomials is convolution on Z, and so essentially you have a standard central limit theorem. The point is that we know from probability theory that central limit theorem, the most important condition is that they're independent. But here they're a little bit dependent. But nevertheless, we know sometimes small dependence will not affect the effect of the central limit theorem. So we can think of these groups, nilpotent groups, for example, as a kind of fibrated by this central series. And we think that, OK, so it's not like a product where exactly knows the central limit theorem. But still, despite some dependence, we might expect that there will be central limit theorem and we'll have a Gaussian, at least in some cases. Now we are numerically checking whether it works or not. In other our experiments, so we wanted to understand the growth and the diameter. There is, for example, one of the works by Jordan Ellenberg and his co-authors, and there was a calculation of the diameter for unitriangle groups. So when we computed it numerically, we see that there is a clearly diameter actually grows linearly. So their result is correct, but as far as I understand, we can amplify it to have a better result, that the growth is actually linear with respect to the n. And just let me mention for the context of why some of these questions are quite interesting. So there is a famous Babai conjecture, which was some progress huge progress by Terence Tao and others. So it's some predictions on the diameters of the finite simple groups. And it's nice to know that for the symmetric groups, this conjecture have very simple formulation. That diameter is something O(n squared. And despite recent progress by Helfgott and others, it's not yet fully proved. So understanding the growth of the finite groups is also a kind of interesting topic, I would say. Now, let me explain about the graph search. So we have what we have discussed, what related to your question, and to give just explanation to this, I want to give some analogy. So imagine two mathematicians are working on the same problem for example, 100 days. And now let us compare it when one of the mathematicians is working on this problem. How many days he needs? The answer from this search procedure is exponentially more days. Not just, so because it's a creative work, if it would be routine work on the pipeline, just the answer would be trivial. So 2 workers, it's do 2 times time, yes? But since it's a creative work like a search, the main point that we exchange the ideas. If you made some breakthrough, you teach me, and I'll start the search from your breakthrough. I will not go into the dead end, which I would go if you didn't tell me. And so this is how this search is organized. OK, let me go into the details. So the key idea is that there is an exchange of the ideas, and then you kind of do not go into the dead ends. So first, OK, so let us remind this search procedure very simple, which I described before. Yes. So imagine you have a graph, and these numbers are the predictions of the neural net. They give you a distance. Imagine that this distance is fully correct. So you start here. you look all the neighbors. This on distance 2, this on distance 2, this on distance 1. So you go here, and then you find a way because this is on distance 0. But now our situation, neural network gives bad predictions. It can be like this. For example, we stand here, we look for the neighbors. So this should be 1, but actually it's given 3. So we should look, for example, we go here. But then we look at neighbors of this node, and we see that we should go there to our initial position. So we'll be stuck in this local minima. We go from here to here, from here to here, and infinite loop. This is a local minima. So this can be explained by this kind of picture. So if it's a ball, then you kind of stacked in the local minima, and you can do nothing. One of the solutions is quite trivial. If you have a small ball, just make a big ball. It's like if you have a mice and you have an elephant. An elephant will not notice that there are some small local minimums. It will just go straight away. So what we need is to kind of increase the number of the search agents. It will help us with the local minimums. Now I want to describe this in details, this search procedure, beam search. It's very simple, but it's very effective, and this is related to this exchange of ideas. So what are we doing? So first, beam search have only one parameter, beam size. This is the number of mathematicians working on the problem, yes? The number of agents which will go on the graph. So first, you have initialization. So that means you choose some B neighbors around your starting node. Then you look for all the neighbors of these B nodes. Then you compute the neural network prediction for all these neighbors. And then you choose B best predictions, best nodes, and you go there. So you choose them not for the one node, but you choose them best for all. That means a kind of exchange of the ideas happens. So so if one finds the breakthrough, this is the point where the kind of distance is changing very fast. All my nodes will go there. So all will follow breakthrough. And they will not go into the dead-end direction. They will come out of these local minimums. This is very simple procedure, but it's very effective because you have these many agents which are working simultaneously. And it's very easy to write in the Python and GPU, and it's very kind of effective.
No, that's a resetting problem. When you run many times with just...
No, but it's different. The point is this is different. Resetting, it's like I am the only person who is solving the problem. Here is the main that we exchange the ideas. We are solving the same problem simultaneously. That's a key idea. Without it, it will not work.
But what specific of mathematicians are engineers or?
Any creative work, not what is routine work for the kind of, we need to repeat something by instructions, yes? So what we mathematicians we're doing, we have some ideas, and I need to explore this idea, another idea, and no? Well, it's everything is relative, but so, okay, I think I need to stop here.
Time for questions, but maybe one quick one.
Do you know about the product replacement algorithm?
Not yet. Can you tell me?
Yeah, well, in general, I had a feeling that there was one word which was missing, which was the word expander. So I think that some things that you have shown should be explained by the fact that the Cayley graphs of symmetric groups form a family of expanders, at least for certain generating sets. And the interesting thing is that there are different generating sets in the symmetric group, as was very recently discovered. For some generating sets, the Cayley graphs will be expanders, and for some, they will be not. Yeah. So it could be interesting to compare growth functions given by these different generating sets, and I think that the pictures will be different for these two cases.
Let's discuss it. It's very interesting, yes, for me.